Hello and welcome to this short video on the fundamentals of probability. Let me first start off by explaining about the sunglasses. This is not actually a style choice. I just had my pupils dilated, and as I'm filming this I have a great big light shining in my face. Plus I think it looks cool. At any rate, let's start off by talking about probability in its sort of most basic sense. There's an equation that I think can take you through so much of probability and so much of basic statistics. And that is this equation. When you're doing any kind of probability calculation, this is really the equation you want to use. You're going to put in the numerator the number of outcomes you are looking for, and the denominator is the number of total possible outcomes. Now, this is only true if all outcomes are equally likely, but you'll find that is very often the case. This is going to come up again and again and again. So I want you to write this down. Number of outcomes you're looking for versus total possible outcomes. Let's take an example for illustration. Let's suppose you're rolling a six-sided die. This is a six-sided die right here, and you're interested in, now I know this is very basic, you guys are going to get this, the probability of rolling a 3. So in that case, we want to know we have one possible outcome that we're looking for. That is one outcome, which is rolling a 3, versus over a total of 6 possible outcomes. So that's rolling a 3. Now, what about the idea of what if we're interested in knowing the probability of rolling an even number? Well, in that case, we have 3 possible outcomes that we're looking for. That would be 2, 4, and 6 over 6 total possible outcomes on that die. Okay, that's a basic example. Let's make it a little bit more complicated. Throughout these videos, I'm going to be using a deck of cards as an illustration very, very often, and I realize this is familiar to most American viewers. However, not everybody plays cards, so let me just really quickly give you a quick overview. In a deck of cards, you've got 52 cards total. There are 4 suits, each of which has 13 cards in it, and that also means there are 13 different types of cards. Ace, 2 through 10, Jack, Queen, and King, and the Jack, Queen, and King are known as face cards because in most decks of cards they have a face on them, as you can see. So of each one of those 13 different types of cards, there are 4, one for each suit. Okay, so we're going to use cards quite often in our probability examples. Let's take a look at some examples of how we might look at this. If with this standard deck of cards, we might want to know what's the probability of randomly drawing, let's say we shuffle up that deck and we randomly draw a heart. Well, we know that there are 13 hearts in that deck. So our probability of drawing a heart out of the entire deck is number of outcomes we're looking for, that's 13, over total possible outcomes, that is, we could have drawn 50, there are 52 cards we might have drawn. So the probability is 13 over 52 equals 1/4. How about the probability of drawing an ace? Well, in that case, there are 1, 2, 3, 4 aces, again, out of 52 cards. And the probability of drawing an ace of hearts, well, there's only 1, so it would be 1 out of 52. Finally, what is the probability of drawing any face card? Well, our face cards are here. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of them out of a total of 52 cards, so the probability of drawing any face card is 12 out of 52. All right, so this is our illustration all of coming back to this idea here. The number of outcomes we are looking for over the number of total possible outcomes that might be obtained. I want to offer one quick caveat to that, which is going to be illustrated by this example here. Let's say we have a class of MBA students, and there are 300 students in that class. 100 women and 200 men. Don't ask me why, but there's a gender skew in MBA classes. So we have 100 women and 200 men in that MBA class. And over here I've listed some of the names of the students in the class. I went ahead and adopted our most typical gender norms. I wrote the men's names in blue and the women's names in pink. I know. But just to distinguish between them. And I obviously didn't write down all the names. This is just a sample. I used the ... to show that I went from the A's down to the Y's and the Z's. What's the probability of drawing, if I just were going to draw one random name from that group of MBA students, let's say everybody put their name into a hat and I mixed it up and everything was even and I pulled out a name, what's the probability that that is going to be a woman? That name is going to belong to a woman. Well, you all know this, it's obvious. It's going to be 1 out of 3. But I don't want you to be confused by this idea of number of outcomes we're looking for over total possible outcomes. Because you might say, well, we're only looking for one outcome, that is being a woman, and there are 2 total possible outcomes, that is being a woman or a man. This is not correct. Actually, what we have is 300 total possible outcomes. We could draw any one of those 300 names, and 100 of those names are women. And so what we're really saying here is, let me give myself a little bit more space here. What we're really saying is on top you have Anne, April, Yesenia, and 97 other names. On the bottom you have Adam, Andrew, Anne, because this is all our total possible outcomes, April, all the way through Yesenia and Zachary. So there's an important distinction. That does not say Zachary. It says something. Zachard. So the important distinction here is when we're talking about a number of total possible outcomes, just because you have an outcome that might belong to some other category or group doesn't mean it's not an outcome on its own. So using this equation, when the likelihood of any single outcome is equal, then you can use this equation. Just be sure you're correctly identifying all the total possible outcomes and the outcomes you're looking for. Number of outcomes you're looking for over total possible outcomes. Can't emphasize this enough. If you get into a bind with probability, remember this equation and come back to it. Thanks.